Hello, geology enthusiasts. We are back for another exciting episode of Geologic Time. So grab your caffeinated beverage and let's get started. So in our previous episode, we were discussing the Devonian. And just as a precursor to the Devonian, you'll remember that in the Silurian, that was the very first time that the continental crust was above sea level. And so that led to the development of kingdom fungi and kingdom plantae. And that was really important because we began to see the development of soil as the diversity and abundance of vascular and non-vascular plants on the planet began to increase. So we're essentially developing a new ecological niche as we move into the Devonian. However, the Devonian was called the Age of Fishes. So it's always termed the Age of Fishes. So we turn and direct our attention again to those shallow marine environments, but this time we're more focused on those epicontinental seaways that are freshwater. And within the Devonian, that's called the Age of Fishes, we really look at the changes that happen in phylum Chordata. So phylum Chordata was first introduced in the Ordovician with the very first, very primitive fish. And so in the Devonian, we really build upon that. So we see the ostracoderms, which is a jawless fish. We begin to see the acanthidans, which is paired-finned fish that has a jaw, but the jaw isn't attached. And then we look for the placoderms. And the placoderms is this giant 20-foot long fish that has this bony dermal plate, and it has serrated jaws and has big eyes. And so it becomes the top predator of those Devonian epicontinental seaway oceans. So the common term for the placoderm is the dunkleostasis, and you find that all over kind of like the Midwest, but specific to like Cleveland, Ohio. So you find it in the fossil record specifically there. And if you've gone to any type of natural history museum, you have for sure seen some type of replica of a dunkleostasis because they are that important to the Devonian and they're that popular. So when we compare dunkleostasis then as a top predator of the Devonian seaways, we can look back to the Ordovician and compare that to the Nautilodea, who was the top predator in those oceans. And then we can compare Nautilodea to the top predator of the Cambrian oceans, which was the trilobite. So over the course of about 200 million years, we've really increased in intensity. And that's mainly because there's so much more diversity in the oceans that it allows for there to be more food. And so it allows for your creatures to become much larger. And so that's what we're seeing when we are moving through the Devonian. Of course, what we said, right? All things come to an end. So by the end of the Devonian, we're going to see a mass extinction. Mass extinction is going to end the short-lived lifespan of the dunkleostasis, so we'll never find that again in the fossil record. And so the question is, well, what led to the end of the Devonian? And what we began to think of is that we've gone again into a glacial phase very quickly, and this time that glacial phase was put into motion by all those plants that began to do photosynthesis on our planet, which we might think is a good thing. But in the Silurian and moving through the Devonian, you've got all these plants, and they're taking in carbon dioxide, and they are, of course, respiring oxygen. But as they're taking in carbon dioxide, they're reducing the signature of heat on the planet. So it throws us back into a glacial phase. What's interesting is we can't replenish that carbon dioxide quickly because we don't have a whole lot of land-dwelling based animals yet. So kingdom Animalia has not exploded onto the land. Instead, in the Devonian, what we saw was the uprising of Ichthyostega as a transitional species, and that led us to the transition of a lungfish or a lobefin fish moving onto land as an amphibian. So the Ichthyostega is that transitional species that connects both of those two. And we're really fortunate to be able to fill in that gap in the geologic record by finding that fossil record. So it really helped to tie those scenarios that scientists and paleontologists suspected as to be a fact. So amphibians started that transition onto land. Remember that amphibians are still tied to water reproduction and also for desiccation through their skins. So we're going to see the end of the Devonian in a mass extinction because carbon dioxide is going to be reduced from all the plants. It's not that carbon dioxide is not yet going to be replaced because there's not an abundance of land-dwelling things on the surface of the planet just yet. So then where we're at today is that we're coming out of that glacial phase, and it doesn't last for long. So you're looking now at an image of what the environments look like in the Mississippian and Pennsylvanian. And you're noticing that we're forming that supercontinent. So still, Gondwana land is moving farther and farther to the north. And when we look at this image of North America, we're still pretty much equatorial. So that's going to give us some indications of what we're going to find as we move forward towards the end of the Paleozoic Era. Remembering that the majority of those epicontinental seaways have dissipated, so they've either evaporated or the subsurface has uplifted, so we lost the basin, and we don't see those as an example. So their habitat for things like ductile stasis also was reduced, and that's what that crowding of those oceans is probably what led to the advancement of amphibians. So North America is posed at the equator. We see a whole abundance of rainfall, especially on the edges of the continent. So one thing that we need to consider is as we're building that supercontinent, you're changing weather patterns, right? And so the internal areas are going to become more dry and your edges are going to trap more of that moisture. And so when we classify the Mississippian and Pennsylvanian, we specifically call them together as a collective, the Carboniferous. So the Mississippian and Pennsylvanian, when they're together, is referred to as the Carboniferous. And it's called the Carboniferous because of the weather and the climate, we see a whole lot of wetland environments that begin to form. And you'll remember when we talked about sedimentary rocks, we said that carbon, when it's under compaction, lithification, it turns into coal. And so that's what we see here. So even where we are in Georgia, the Carboniferous is really important because that's where we get our coal from to burn for electricity. So most of our coal comes from West Virginia. And this is just an illustration. What's important at the 101 level is something that's called the rain shadow effect. So anytime that you have high level elevations on your edges of your continent. So at modern day, if we're considering the Pacific Coastal Range on our west coast, so the Pacific Coastal Range contains like Mount St. Helens, Mount Baker, Mount Rainier, some of the bigger volcanoes in our United States, and some of our elevated topography is part of like the Rocky Mountain North American Cordilleran. So when water is coming from the Pacific Ocean, it runs into the Pacific Coastal Range. And so it can't go up and over because the elevation of that range is too high. And so that's why, for example, like in Seattle, you get a ton of rain, but then on the backside of the Pacific Coastal Range is Spokane, Washington, and it's relatively dry. And it's because the precipitation can't go up and over to the backside of that mountain range. So we call it the rain shadow effect, and that's what really dominates in the Mississippian and Pennsylvanian. And in the Appalachians, as we saw in this last picture, they're truly beginning to be formed. So the northern part and the southern part is going to be formed by the end of the Pennsylvania when you have the collision of Africa. So in the Mississippi and Pennsylvanian, when we're talking about the Appalachian mountain range on our east coast, we consider the Appalachians to be as tall as the Himalayan mountain range. So we're talking significantly taller than what they are today. And that's because they've gone through about 300 million years of erosion. So this was like the heyday of the building of the Appalachians and the building of those coal beds that are really important for energy as a resource. Here's a picture of a cross-section of a coal seam. if you ever get the chance to drive north up to the great state of Michigan, you get to pass through Kentucky, going on 75 headed north, and you can see just fantastic pictures of coal seams. And so what you're noticing is it's not too deep below the surface, probably less than 100 foot. So it is accessible, and that's where between Kentucky and West Virginia, that's where the coal for our area comes from. I like to show this little schematic on the screen just to give you a feel of what the Mississippian and Pennsylvanian might have looked like. And you see all of these, we've developed those vascular and non-vascular plants during the Silurian, and now they're really starting to take hold. And so in the Silurian, we saw the lycospid tree, for an example. And so the lycospid is kind of like a palm tree, a soft tree, but is able to grow about 100 feet or so tall. And we began to see the very first hardwood trees. So you're considering this North America, being towards the equator, you're developing these swamp-like regions, and it's a really important phase of geologic time. So now we're going to move into the excitement of what is Permian. So the Permian is going to be known as the rise of the reptiles. And this is what you've waited for all semester, right? Is to talk about the rise of the reptiles. So in the Devonian, we saw the transitional species of Ichthyostega moving from that lungfin fish that was in the freshwater environments, moving to land as an amphibian. So amphibians and reptiles are very similar. The difference between them is the amniotic egg, so the origin of the amniotic egg. And so this is what we see for the very first time in the Permian. So just as an example, I'm going to move forward a bit. When we think in terms of amphibians and reptiles, you can make a comparison between a salamander, which is at the top of this picture in red, and a lizard. So a salamander and a lizard visually look similar. The difference is, remember that with an amphibian is tied to water for reproduction, and they have a skin that can desiccate. So although they can go onto land, they still need a wet environment. So the beauty and the complexity that we see within the Permian is the origin of the amniotic egg. And so this means that now for the first time, we are going to see signatures of kingdom Animalia that can be on land. Moreover, not only can they be on land, they're able to move away from those water sources. So, and that's because the amniotic egg provides its own food source, and it provides a shell to prevent it from desiccating. So this is going to prove to be a huge advancement in the geologic record. And so not only do we see evidence of reptilian life in the fossil record, we also see evidence and find fossilized eggs. So we have a really good understanding of how this moved forward. So when we start to talk about the rise of the reptiles, we're not yet thinking about the big dinosaurs. We're thinking in terms of building up the complexity of smaller reptilian life. And some of those that dominated within the Permian is going to be like Diplovervin, which we see on the screen. So Diplovervin looks a lot like a crocodile or an alligator. It's more like a crocodile because it can be in saline environments. But the whole moral of the story is that it has similarities of what we saw in the amphibian record. So we're thinking in terms of that easy transition in terms of hymology and vested structures. But the complexity is that these guys are going to be much more of a predator. And this will be a theme that we kind of see throughout, is that we're really going to focus on the brain cavity in the shape and position of teeth, because that's how we're going to help. One of the means that we're going to determine whether something is a scavenger or something is a predator. So like where they're hanging out in the food chain. So what we're going to see then quickly, because we do see these advancements in teeth, and knowing that a reptile can move in other parts of the land away from water, they're going to become the top predators very quickly over amphibians. So we're going to see great advancements in the Permian with blade-like teeth, and even like an ectoskeleton that can not desiccate. In addition to Diploveribin, we also see the Pluckliosaur. And so the Pluckliosaur is really a common fossil. We would call it an index fossil because we start to see them in the Permian, and they're going to quickly go extinct. And what's interesting about the Pluckliosaur is the Pluckliosaur is considered to be a transitional species between a reptile that we just saw and a mammal. And one of the things that paleontologists believe is that the Pluckliosaur is mesothermic. So something that's mesothermic is in between something that is ectothermic, that is cold-blooded, like an amphibian or a reptile, and something that is endothermic, which is something that is warm-blooded, like a mammal. So it's thought that the Pluckliosaur was a transitional species whereby they were mesothermic, meaning that they had the potential to regulate their temperature. So as an example, like a reptile that is ectothermic, they're cold-blooded, so they have to have a heat source in order to keep them warm. They can't produce their own body temperature like a mammal does. And so that's why if you have if you have a snake or a lizard or a frog, you have to provide them with like a heat lamp because they can't produce their own body temperature. Whereas something like a mammal, we're able to regulate our temperature, right? We're humans, we regulate our temperature at about 98.6 degrees. So the Pluckliosaur is something that's in between those two. And so when you look at the pictures, you see this, that they have these fans, and it's thought that these fans are acting like radiators. So if they are, if they're cold, then they put the fan down, and if they're warm, they put the fan up, and it allows for the heat to expire from their body. So it's kind of like a radiator system that allows them to increase or decrease their temperature depending on their needs and their environments. So it's a very interesting adaptation. So just kind of recognize like their fan is collapsible. So you can put it up or you can put it down depending on your temperature needs. And additionally, like we mentioned, that we're going to focus on the skull and the skull cavity. The Pluckliosaur has mammalian-like features in their skull. So we're going to come back to Pluckliosaur later when we talk about the uprising of mammals, but we do see small mammals in the Permian record. And we'll talk about this when we talk about the uprising of dinosaurs. They're going to be quite small. So we're thinking in terms of like no bigger than a cat. But by no means are they abundant. This diagram here is giving you some imagery to kind of think about a mesothermic animal versus an endothermic versus an ectothermic. And so they're showing you some modern and prehistoric examples of those. So whether you're looking at sharks that are ectothermic, or if you're looking at a horse that is endothermic, and then you've got the dinosaurs that are in the middle of that. And there's this is still something that is debated as to whether dinosaurs are Mesosauric, but a lot of the teams nowadays lead towards that in the research. So in the Permian, we are truly invading into the land space. So we're going to start to see adaptive radiation with these different types of reptilian species. But one thing we haven't talked about yet is what's happening in the air. What's happening in the air. And so in the Permian record, we see fascinating examples of insects. And we're talking like major insects. We're not talking like little insects. We're talking like that we saw in the Silurian with the development of with phylum Arthropoda that was moving on land in the soils with scorpions and spiders. In this case, in the Permian, we're seeing like giant winged animals. So we're talking about like dragonflies that have a 6 feet wingspan. So just like these massive insects, millipedes, like 3 feet long millipedes. We're seeing like this crazy advancement, almost similar to the Ediacara and biota, where you're seeing these like bizarre adaptations, because this is the only time we see large insects on the planet, and we don't see them for very long. So they're there, but then they're going to go extinct. So the question remains then, why do you have these very large insects? And it's probable that there was more O2 in the atmosphere. So right now we have, we've got 70% nitrogen in our atmosphere, 21% oxygen in our atmosphere. And so in the Permian, it's thought that there was probably more than 21% oxygen in the atmosphere. So there was more abundance, and these large insects kind of like played on that. So they have different breathing systems that are a little bit more complex, with the ability to take in more oxygen and use that as a tool for flight, especially in the case of a dragonfly. So these would be considered like our very first aviators on the planet. Here's a fantastic picture of one of those dragonflies. And what you'll remember, like when you're looking at this picture on the screen, is that it has to be an impression, right? So dragonflies have a little bit of an ectoskeleton, but it's that fossil preservation of impression that allows us to be able to see those signatures. And they're stunning. Like if you get to see them in person, the Natural History Museum in New York has some great insects and the giant dragonflies on display. So all good things come to an end. Again, the Permian was so exciting because we saw the development of the amniotic egg. We saw the uprising of a true reptile, and then we got to see a transitional species in between a reptile and a mammal, with something that has Mesozoic type of features. So the Permian extinction, man, this one's a doozy. So the Permian extinction is going to be considered as the most severe extinction ever. So ever in the fossil record, where we are going to see 95% of all marine species die. Over and out. 95% of all marine species are going to die. There's not a whole lot of species that have really diversified on land, because they just haven't had time, because we just saw their uprising in the Permian. And remember, we're coming out of a glaciation. So write this down. So this is the most severe extinction found in the geologic record is at the end of the Permian. The second largest is at the end of the Ordovician. So Permian extinction is the largest, Ordovician is the second largest. When we look at the organization of families, we're going to see that 80% of all vertebrate families are going to go extinct. And remember, we're thinking in terms of phylum Chordata, mostly, that is in the ocean. So all those fishes that evolved in the age of fishes in the Devonian become extinct. And remembering, they just rebound as they came out of the Devonian extinction. Then they rebounded in the Mississippian and Pennsylvanian, and now they're taking another big hit. And so this catastrophic event is going to mark the end of the Paleozoic Era. So we've gone from 570 million years at the start of the Cambrian And then the Paleozoic Era is going to end at 245 million years at the end of the Permian. And so remember, very first day of class, we asked the question, what change shifts us from eras? And it's mass extinction. So this is the largest event on record, and it's going to wipe out 95% of all marine species, 80% of all vertebrate families, and it's going to be devastating on the planet. So our question, of course, then is why and what happened to cause this mass extinction? So I'll let you think about that for a second. What's causing this mass extinction to happen in the Permian? So lots of times it has to do with climate change, but then the question is, well, what's forcing the climate to change? So in this case, the Permian extinction is a little bit different than ones that we've already talked about. And that's because it's going to happen over a phase. And the extinctions at first are going to be concentrated in tropical environments. So in the Permian, we're just about completely formed our Pangea. So we're going to have a little bit more movement north as we go into the Mesozoic, and then we're going to start to see the breakup in the Triassic. So we're almost there. We're not quite there, but this extinction is different because it's first going to be concentrated in the tropical environments, and then we're going to see like a wave kind of radiate away. So it's happening over a longer period of time, which is different than like going into the Ordovician glaciation and coming out of it, going into the Devonian glaciation and coming out of it. So the wave of extinction is going to happen a little bit more gradually, is what we're trying to focus on here. But again, what's causing this unusual situation in the Permian? And we can look at our Pangea and ask some questions. What I'm going to do is I'm going to let you think about those questions about what you might have of the Permian mass extinction. And what we're going to find is that volcanism is going to be the biggest part of the story to the Permian extinction. So there's something that's called the Siberian lava traps. So a lava trap essentially is when you have fractures and fissures and a hot spot, and you have all this magma come up to the surface for an extended period of time. So what we know about magmatic events is that they bring a whole lot of carbon dioxide to the surface very quickly. Carbon dioxide, sulfur dioxide, carbon monoxide. So you bring all of these gases up to the earth, and those are all greenhouse gases. And so you're going to see a very quick and abrupt warming period. And we're talking about as much lava coming to the surface that could cover the entirety of the United States 2 miles deep. And this happens over the course of about 1 million years. So it's a significant climate change event, very different than what we've seen prior, because we've seen us go into these glacial phases, but we've never seen us go into a warm phase. And so it is that warm phase that's going to cause some devastation and extinction at the tropics, because the water temperatures just get too warm. The planet gets too warm too quickly. What I'm going to do is I'm going to post a video for you to talk a little bit more about the Permian extinction, because I want you to see what those changes actually look like in the fossil record. So I'm going to pause here. You've been a wonderful audience. Our next episode is going to focus on the Mesozoic. So get ready for some dinosaur action, because I know that you'll love that. Have a great day. See you later.